Hello, I'm Habip Kenan Üsküda from Axon Networks. I work as a DevOps engineer, and I'm also responsible for our cloud platform's observability. Today, I'll be presenting about our use of Pulsar and how we establish its observability, where we deal with high-topic cardinality deployments in the telecommunications field. Before I start, here's a bit about myself. I'm primarily an integration engineer who architected and developed systems and software solutions over the last decade. And I'm currently responsible for building and maintaining the observability stack of our cloud platform within the telecommunications space, where the event fabric of the platform runs on Apache Pulsar. As part of the session, the agenda will be as the following. Firstly, I'll go over our use case scenario in utilizing Apache Pulsar, where I describe our requirements and how we utilize it as an event fabric, and then emphasize the restrictions we experience for the metrics backend we had set up for it. Following this, I will talk about our solution description and how we were able to go beyond this limitation for the classical metrics backend through our own approach and what that entailed. Finally, I'll be going over the fruits of our labor in the results section and present you with an overview of the future work planned for the observability stack, and then we'll take your questions. So let's go over our use case scenario of Pulsar for our cloud platform in Axon Networks. Pulsar is used as an event fabric for its promise of high throughput and latency for our software as a service orchestration platform offering, which is cloud native in terms of its implementation. The platform, and term Pulsar, supports transporting our proprietary VH protocol using messages. Now, through this approach, we support autonomous onboarding of our physical edge customer devices as virtual CPEs in the manner of providing a secure access service edge deployment. This deployment enables each and every device to have its digital twin residing within the platform, be it on bare metal or on the cloud. The communication itself is secured through a mutual transport layer security scheme of certificate exchange. And this is done per every device on separate channels. With this, compute-intensive tasks that might not have been possible on individual CPEs are delegated to the cloud-native platform. And the outcome actions for each CPE in turn are messaged back to the individual device through its own secure channel. To this end, the platform observability should be capable of granularity per device channel. We have current and planned deployments ranging from supporting 10,000 to 1,000,000 devices. That might seem like quite a large target, yet it is a reality for us by the end of Q3 of 2023. So, moving on to the part in terms of what happened in trying to set up the observability for this. Now, as anyone does in a cloud native setup, we started out with the Prometheus stack, then tried federated deployment of Prometheus, then Victoria metrics, and then out of box Mimir to handle ingesting the metrics from Pulsar. Primarily, it's brokers that end up being the headache, causing the headache for us. But to no avail. For each one of these, it would start to go unstable every time we were trying to host more than 2,000 channels for our CPEs. And when going beyond 5,000 channels, we had the metrics backend crashing on us. Through this journey, we came to the realization that the way how Pulsar metrics were labeled for each channel was tied to a topic level that pushed the cardinality to a level for the metric backend that it could not handle. Now, to overcome this, we needed to identify the root causes of what was going through with our way of ingesting and recording these time series records. Because the label cardinality at the end of the day was just one part of the issue. Now, those root causes were firstly, the metric backends used a bulk approach in scraping the metrics for different application workloads and had lacked the ability to have granular control while being centralized, which yielded a single point of failure. In addressing the solution description for this, I'll put emphasis as how some things differ with regards to what you could say configured with Victoria Metrics agents, if anyone will end up having a question with it. Nonetheless, let's go into the second root cause. Now, when we're seeing that we were both consuming high amount of resources while trying to ingest these metrics when we're going over these 5,000 channels for the 5,000 CPs, a question dawned on us. Was every metric being scraped, or those that were bundled together, necessary for us to ingest? And what would it take to split them and filter them out after determining what we needed out of them? The reason why this is a root cause is tied to the issue of we have series that have these specific labels that cause this high cardinality, while there are also series that get published from the same endpoint that would not. So we needed to have a way to filter these out and even distribute them, perhaps, into different metric backends. So that's why this is a root cause as to what would it take to filter out or just drop any unused metrics selectively so that we'd be using our processing power where it's needed. And as the last root cause was the issue of the high metric cardinality on metric series labels for which the metric backends were not built to handle at scale, at least out of the box. Worse yet, this root cause was not only limited to the metric backend, but also prevalent in visualization as well. The Grafana that we use for visualizations had its filters on dashboards and legends on panel would have issues in rendering more than 4,000 unique values on them. So all in all, this last one is a root cause we need to address for both metric backend and the visualization side, for which we did. I mean, yeah, this all looks bleak, or at least it did back then, when we did not have our solution. But this session is all about that solution description. Now, in tackling these restrictions and addressing these root causes, we ended up with an initial plan in 3 stages to implement a solution reflecting the root causes in tackling them to make a transition that you are now seeing in this slide. These stages are basically to build out what we call a Grafana agent stack for granular control, then implement metric series filtering for optimal metric processing, and lastly, to strategize and implement a remapping strategy to regulate label cardinality. Now, let me dive into it. First stage was building out the Grafana agent stack for granular control. So, for those who might not be familiar with it, Grafana Agent, an internal Kubernetes operator, is an open source project by the Grafana Labs. This project provides setting up agent instances for metric scraping. These instances are essentially lightweight Prometheus instances. Operating in agent mode, send metrics to a remote metrics backend. Now, out of the box, there's not an agent stack. But through the magic of Helm-based templating, we built one. Now, this stage involved setting up granular approach for the metric scraping. And this is in contrast to having a single large Prometheus instance or a Mimir doing service discovery to scrape everything. This can be set up so that based on service or pod labeling, everything can be grouped into an agent, and in turn, a metric scraping instance to target a specific group of metrics within each instance's operation. All in all, this enables us to categorize our own scraping backend at various different levels. One of them is cluster common workload scraping, such as that for the general container metrics and Kubernetes metrics, or the application infrastructure workloads scraping for the ingress and databases, or the application service workloads for various microservices or individual Pulsar components, and even per series instances in which a metric instance can scrape and send either a single or multiple but selectively grouped metric series from an individual component of an application workload. In our case, this was the Pulsar Brokers series. Now, having this level of granular control provided us with establishing separation of concerns for metric throughputs from different workload sources. This in turn enabled us to actually establish a baseline for custom configuration for service or pod monitors, or to have rule-based customization that would have the capability to make it possible to group certain metrics groups to be sent to different metric backends, and separate metric backend targeting for each one of these metric instances in a one-to-many targeting scheme. Now, this draws on from making use of the rule-based customization, but especially for the per series metrics, what was essential was to group certain metrics together for general use, together with that of the application workloads, and specifically for the Pulsar itself. So, having this also enabled us to target various different metric backends from which we can integrate with, so that we would not have to worry about a metric backend going down and basically taking every other part of the observability stack with it. Obviously, this stage also enabled the next one, as these stages are built on top of each other. And the second stage involves the capability to implement metric series filter for optimal processing of the metric series. As following from the first stage, this enabled us to be able to establish a structural way to filter and control our metrics pipeline for the cluster common workloads, the application infrastructure workloads, application service workloads, and even per series instances in which a metric instance can scrape and send either a single or multiple selectively grouped metric series from individual components of an application workload. Again, our case for this is generally for the Pulsar brokers series. Now, this was critical as you can use the templating approach to have granular control over our diversified metric scraping instances to establish rules on selection and filtering. This is vital in overcoming the lack of negative lookup on regular expressions that is intrinsic to the Go library used in various metric backends for the relabelings and metric relabelings. This in turn enables various new characterization levels for metrics on different deployment targets based on what rule needs to be applied on rather than only what service or pod monitor we are trying to script the metrics for. So we are not bound by what a singular instance can do, but what we can do at even a service level to define an agent instance that can script things from a pod for even a single metric series. Now, I went through describing these two stages for the next, which is the part that was milestone in resolving the issue of cardinality. However, that stage would not have been possible if the framework for granular control and configurability was not set up through these. So here's the third stage in establishing our solution, our remapping strategy to regulate label cardinality, which is the fancy way of talking about how we can deterministically and reliably split our labels to abolish the issue of high cardinality. So first things first, we have the rule groups to determine between configuring agents that distinguish between whether if the target's being scraped by subject to the label type that can have high cardinality. Then within those groups, we determine whether if the label can have a high cardinality and in turn apply only processing in the metric instances in the latter. Now, describing this is rather simple, but the result is powerful, as the remapping we do selectively targets and reduces a label value set that can have a billion unique values to be decomposed into sublabels that can only really hold 100 unique values. Now, though the implementation itself is quite unique, the idea basically is to have a pseudo subnetting of our channel IDs. And with that, we're able to reestablish our observability when we had high cardinality in our metrics. And the results are the fruits of our label in the form of some colorful dashboards. First off, this is a capture and utilization of non-high cardinality label values of a different labeled subgroup that has high cardinality metrics. We subgroup these as non-serial type messaging metrics. It is primarily used to monitor the throughput processed in terms of both in count and size of messages passing through the entire event fabric. Everything except the individual channels. This is a dashboard that we view 50% of the time when we are monitoring our platform. Second is a capture and utilization of non-high cardinality label values of the same label subgroup that has high cardinality metrics as well, but we subgroup these as serial type messaging metrics. This is a dashboard that we view when we want to monitor whether if there are anomalies within the channels from a summarized perspective. And lastly, this is essentially what remapping enabled for us: capture and utilization of high cardinality level values through remapping of labels. We can selectively browse and target the monitoring of each channel at an individual level with them. Obviously, not everything is always perfect. And then as engineers, we try to conform to having the optimal solutions. The optimal aspect is obviously a balance between implementing functionality and doing it in a timely manner. And I might end up cutting into the Q&A portion for this next one, but the latter aspect generally means cutting out certain parts. And for that, I have the future work slide that I will go through rapidly. As our primary problem was tied to being able to process the metrics, the solution basically focused on the tail end of our pipeline. However, the moment we had established it and had the ability to scale further, we had noticed that specifically the Pulsar broker serving them started having issues. Approximately for every 1,000 of our device channels, a broker generates around 2 to 4 megabytes of metrics payload, and this size scales quite linearly. This is a substantial load on the broker pod, and observing its adverse effects on it, we had to increase our scraping interval to 75 seconds from the original 15. Furthermore, we had 70 agents scraping individually for each series from broker pods. This meant 70 individual requests to each pod every 75 seconds. And that caused a substantial load on it. To tackle this, we have consolidated those agents to be 6 in total. Now, this, although this would reduce the load on the broker itself, it ends up shifting the load on the scraping agent and its target metric backends as well. So it still needs to be addressed. And to tackle this, we are currently in the works of implementing what we call a metric exporter proxy and its Kubernetes operator to cache the metrics response from our broker in configurable intervals that will also adjust the TTL of the cache, so that we can go back to having individual agents for the series with increased resolution without increasing the request load on the broker pod. Second one is a metrics aggregator, which is essentially an integration service that will serve metrics by evaluating ProQL queries that we need to aggregate specifically for individual egress channels. Currently trying to perform this in Grafana, or the layer that evaluates alert rules, can't scale and weren't built to do so. And trying to hook into them through the scraping agents or additional targets is not so feasible, even though it is currently how we are trying to handle it. This is the metrics aggregator will play a large role in terms of the robustness on evaluating alerts, as well as how we integrate with the horizontal pod autoscaler for our services. And third and the last one is quite the ambitious project. With it, we seek to offload the evaluation of metrics from the broker pod itself to a sidecar container or a different service altogether. Our first experimentation with it involves using both the JMX interface of the broker pod's runtime and a aspect-oriented tracing harness-based agent to break out what is originally used for evaluating these metrics from out of the broker pod. And that's about it. I thank you for your patience, and we'll be taking your questions in the next 10 minutes. Or what was supposed to be 10 minutes, and in turn now 5 to 6. You can reach out to me through my personal or business email for any further questions. Questions, queries. So before wrapping up, I want to extend some special thanks to our platforms team in Axon Networks, comprising of Vito Sansevero, Arman Gürkan, Alperen Çelik, Dat Wang, and Mark McCarthy.